Hello, hello, hello. All right. Who's my first hello? Can I get a hello? Thank you, Kaya. Excellent. Good afternoon, Kaya. Oh, now we go. All right. Wait, wait. All right. Awesome. Good afternoon, Kaya. Thank you. Good afternoon, Ariana. Thank you. Good afternoon, Sydney. Thank you. Good afternoon, Yaneli. Thank you. Good afternoon, Genesis. Thank you. Good afternoon, Erica. Thank you. Good afternoon, Samantha. And thank you. And good afternoon, Gabrielle. Oop, sorry. Gabriella, thank you. And more people come. Okay. Um, all right. So, double good afternoon to Gabriella. Rock and roll. Awesome. Thank you. Now I'm actually teaching. Hello, Karen. All right, that's all. And she's actually learning. Okay. Good afternoon, Sonam. Excellent, excellent. Okay. Oh, and more. Okay. Okay. We are happening. And by we, I mean Gabriella and me. No, just kidding. That's so okay. All right. Well, at least you like that. All right. Um, and see if the rest of you are mad that I said that. I can't tell because you're not showing. All right. Anyway, all right. So we're gonna get to physics today. What's the deal? First of all, you guys have been totally on top of homework. I appreciate it. Like things are coming in, revisions are coming in, people are getting more and more points. I see the improvement, blah, blah, blah. We're all, and I think anything anybody's turned in at this point, I think you've gotten back. I mean, unless you just turned in the last 10 minutes. And the thing that's technically due right now, due Wednesday, is homework 6, which is big old duck. But wherever you are, just keep going, et cetera, et cetera. Um, so first of all, so what's going to happen today and what's happening over the next couple of days? So first of all, um, we've been solving problems in homework 4 and 5. We have one last problem left in problem 5, in homework 5. Strictly speaking, you all went over it already in a video that you watched. So I'm going to be somewhat concise about it today. I hope, sort of concise about it today. The idea is that already in a video that you watched, you've seen what the significance of the last problem of homework 5 was. So in principle, we're ready to move on to homework 6. However, good afternoon, Brian. Thank you. However, I mean, video is one thing, class is another. So what came out of the videos you were watching was a bunch of new equations that are now super useful and important for homework 6 and for the rest of our lives in physics. So the emphasis of today, once I get rolling, the emphasis of today, and good afternoon, Joran. The emphasis of today is to let the two more people that are in the waiting room in. The emphasis of today is that there's really like, well, the emphasis of today is the following, is this, what's on the board now. These three equations that are on the board are unfamiliar to you if you didn't watch the videos that you're supposed to. Okay. And if you didn't watch the videos you're supposed to, then my run through today might be faster than you would like. So please watch the videos. Um, but I am nonetheless today in a few moments going to try to summarize the where those three equations came from, what the purpose is, and add them to your ongoing list of possible step 3 GDPs. Okay, so today is mostly going to be about equations, like what equations we have so far, because now the list is starting to get longer. It's starting to look like physics, right? So, and people have all kinds of relationships with equations. I want to get straight exactly where we are with the equations today. So it's mostly about equation development or manipulation today. We won't actually solve any problems on a practical level today, for good or for bad. Um, um, and partly this is also in response to things I've been seeing in the homework and where I think you're comfortable with the equations and where not. So I'm going to turn the page in a second, but there was so these equations is the goal for today. Oh, yes. So, but also I want to say, you notice there's three equations in yellow here, but right above them in white, it says IFF A equals A naught then. Okay, so first of all, whenever I write IFF, I mean if and only if. So that's a very strict kind of like for any of these equations to be true, it must be the case that a certain condition is met. That condition is A equals A naught. What does that mean in English? It means that whatever the acceleration is at any given instant is the same as what it was at the very first instant, like of any problem or any experiment. So that's a mathematical way of writing that acceleration is a constant. In other words, everything we're dealing with now in class and in lab is this branch of physics known as constant acceleration. Let me back up even further, especially if anything I'm ever saying to any of you is like not clear the way I'm saying it. We don't have a required textbook, but if you're ever trying to look things up and get help from Khan Academy, or which I highly recommend, or other websites like that, or like a tutoring center, or blah, 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 and you or a textbook that you optionally have purchased, what like how do you look up like what we're doing? Like what are we even talking about? Or is this just like Yaverbound fantasy land? The topic that we're in right now, the larger chapter of any physics book, is called one-dimensional kinematics, 1D kinematics. That means the principles and definitions governing motion in a straight line, one dimension of space, right? That's where we're at right now in general. By the time you get to lab 4, and by the time we finish the problem called Big Old Duck at the end of the homework 6 entitled Big Old Duck, by the time we get to the end of Big Old Duck and you've done lab 4, then we will have transitioned ourselves to two-dimensional kinematics. That's the next topic. Why I'm saying that, two reasons. Number one, our goal in all of this, like the homework, I think is starting to get more like real or customary looking and more hard, maybe for many of us. And the labs are starting to get more involved. Where this ship is heading with all these equations and all this practices, the ultimate goal is to be able to solve that problem called Big Old Duck at the end of the sheet called Big Old Duck. That is a hard problem. Many of you did a great job already. And technically it's due this Wednesday. Many of you have already handed in some drafted homework where you did a whole bunch of great stuff on all the early problems, and then you sort of like, like gave up on the last one, which I totally understand. It's a big leap forward, that last one. It is our ultimate goal. And so if you've gotten some points, you could still get all the rest of the points, like once you've done that problem. What I want to caution you though, we're all going to do it together. That's our goal. Not today, but like next week. And then once we've done that, it's time to move on to two dimensions. But what I want to caution you that even though that problem is hard, and even though that's where we're directing ourselves, if you really start taking seriously the 5-step method and seeing the purpose of the 5-step method, you'll see that even a hard problem like that, maybe you can't envision how to get an answer or what the answer is. Neither could I when I look at that. But you might not see like the light at the end of the tunnel of that problem. But the whole purpose of this 5-step method is it gives you a bunch of things to do to get your journey going without necessarily knowing where it's going toward. Like, so you can do step 1 for that problem. You can make a picture and label everything. And you can make all the facts of the problem. And even if you don't even if it looks like a really complicated situation, by drawing it and by writing down the facts, you'll start being able to picture the situation. And then you write down step 2, like what is the question that thing is asking? It's like, it doesn't seem even obvious at first what it's asking. But if you literally force yourself to write down in your own words what the question's asking, then by the way, you've already done 40% of the problem according to them. You've done 2 steps out of 5. Then step 3, now start even if you don't know how you're going to use your general definitions of principles, I'm about to give you a full list of every legal step 3 that we have so far in this class. So choose 1 or 2 or 3. Like there can be more than one. In step 3, you can write down more than one thing, but what you write down have to be general definitions and principles. I'm going to outline them in today's class. So you do that, and then in step 4, start manipulating what you wrote down in step 3, even if that's as far as you get. I'm going to tell you 2 things. Even if you start manipulating things in step 4, and then you hit a wall, two things. Number one, you've done a huge amount of the problem already without knowing what to do, right? Like literally without thinking that you know what to do, you've done a huge amount and gotten a huge amount of points already. If you know, if it, and you would if it were on exam. And very likely by the time you get to the middle of step 4 and hit some kind of wall, the truth is, I bet the wall will start moving. If you're already rolling now into step 4, the wherever you thought the wall was originally is going to keep moving out because you're going to keep doing things to generate more things to do. So this is a long way of saying some people have already handed in homework, and that's awesome. Or when you do the homework, if you get to the last problem and you think, I have no idea what to do, we're getting to the point in this course where that's not an acceptable. I mean, it's an acceptable first emotional reaction, but it's not an acceptable thing to do on the page. Don't just leave it blank. There's tons you can do to get yourself going, and that's the purpose. So now that you've practiced the 5-step method in places where it seemed unnecessary, for many of you, the big old duck problem is exactly where it's necessary and helpful. And then even if, quark forbid, you still don't finish it, even if you don't finish it and get an answer that you're confident of, what you do is wherever you get to, now say, literally, I don't know what to do here because I don't know how. I need blah quantity and I don't know how to get it. Like literally, don't just trail off. Don't just walk away. Literally put a seal on your work by saying, here's why I'm stuck. Because I've done this much. I clearly need blah, but I don't know how to get blah. And first of all, that's like a really honest and helpful thing to do that shows you're not just like that you gave a valiant effort, but also, again, quite frankly, if you literally articulate exactly what the issue is, 9 times out of 10, then suddenly you're like, well, then I guess I could use this equation. Like it will push you forward. Anyway, so that's first of all, that's advice about the last problem. Second of all, that's due on Wednesday. Anyway, you get my point. But then second of all, you'll notice what's intimidating about that problem, maybe, is that it seems like it's in 2 dimensions. I mean, there's like a duck going like this, and then there's like a bullet that's going like along a different axis. And that is also what's intimidating about lab 4 is it seems like suddenly in lab, I know you're not up to lab 4 yet, but or even lab 3, sorry, I always say, or even lab 3 seems like suddenly we're exploding into 2 dimensions and we haven't learned anything about how. But that's how physics goes. You experience something and then you try to figure out what you're experiencing. So the big hint for both lab 3 and the big old duck problem is that yes, they're a leap forward, but they're not like meant to be unfair or to make you angry. The underlying principle is if now we know how to do things in 1 dimension, then let's if you're faced with a situation that has 2 dimensions, just deal with them 1 dimension at a time. Just analyze each dimension as its own thing separately. That's like, I mean, I'm going to be more specific about that, but I mean, just like people when they first encountered 2-dimensional physics, having only established 1-dimensional, what did they do? I mean, they didn't have someone to give them a formula, like they had to reason it through, as will you. So the last reason I'm mentioning all this is all these equations that we're getting now, yes, they're part of a larger topic called 1-dimensional kinematics. Every one of these equations in and of itself is meant to apply strictly to 1 dimension of space, to something traveling along a number line. But also now that we're introducing this condition, the white condition, A equals A naught, that means that from now on, these equations are only true when acceleration is a constant. So if you're ever looking up these equations or looking up more help about them in Khan Academy or something like that, and this is not a paid advertisement, I mean, whatever, in wherever you look, you could type in constant acceleration equations. That's what these are. They are known as the constant acceleration equations, and they only apply in and of themselves to 1 dimension of space. Okay, so that's what we're gonna be expanding on today. Yeah, okay. So my goal is to make some sense out of these equations. In order to do that, I'm turning the page and I'm saying, here's what we have, and I'm changing the view on the screen. I'm saying on this page, is what we have so far, like before you watch those videos of last week, like as of the middle of homework 4, average acceleration, these were the things that we like know or have established in the class thus far and now know. In other words, everything on this list is acceptable as a to use as a step 3 GDP when you're doing the homework. Um, including like Galileo's principle of relativity. Like it's fundamental to all these fundamentals. It's in English so far. There's 3 different forms of it. I haven't written them all out here, but you have them in your notes. The 3 different forms of Galileo's principle of relativity is a principle. It's a fundamental idea from which you can derive any idea you need for a particular step 4 of a particular problem. That's also true of these other more mathematical looking things. Notice, like A is a principle because it's true. It's so fundamental. It's like it's true even before the law, even before we establish all the laws of physics. It's just literally saying what the laws are going to look like or obey. And then these other equations are so fundamental that they're definitions. I'm not saying all GDPs are always definitions. They're called general definition principles, but these all are. They're true. If they're true at all, they're always true. And they're true just because they're stating how we use language. Like, right? Now, 2 of them, granted, C and E, what they're really saying is that the instantaneous velocity as a physics concept can be defined, can be understood to mean what we call in calculus the first derivative of position with respect to time. Like it's just linking the physics language, the physics content with the math language and saying, what do we mean by v without a bar on it? We mean v with a bar on it taken to the limit. We mean not the slope of the position time graph between 2 points, but the slope at a position time graph of 1 point. I mean, the slope at 1 point of a position time graph, i.e., the slope of a line tangent to a position time curve at 1 point. And that's known in calculus as the derivative of the position with respect to time. And similarly, a definition of acceleration. Now, those are hard to plug and chug directly into. I'm not suggesting that you can sort of do algebra or something on those 2 equations, but they are fundamental. And often you start the analysis of a problem with recognizing that I need to take a derivative here or whatever. These are now, to be super honest or whatever, I mean, the ones of all of this whole list, so anything on this list is acceptable to use as a step 3 GDP from here on in. To be sort of practical or honest, I would say this one here and this one here are the ones that most commonly then just turn themselves into clear algebra in step 4. Like they are, oh gosh, and there should be Yikers Island. Hold on a second. There should be. That's also not what I meant to do. Sorry. Okay, there should be a bar over there. I hope there was for the other class. Those 2, when in doubt, when you want to think of something, you just want to get going, like if either of those applies, try that first because they immediately start generating algebra and stuff. Now, so this is what we have so far, and you're welcome to ask any question in the chat, but this is what we have. We have 5 equations, 5 principles, entering in to the next stage where I generate 3 more on the videos. One of the reasons I'm making a big point that these are our GDPs is the homework, really, you're doing a great job keeping up with the homework, trying it when it's hard, retrying it when it gets easier, all that kind of stuff, and keep them coming. I'll still accept revisions. I will still accept revisions for more points on anything. I hope that's clear. But one theme I noticed in the homeworks in both sections is that a lot of times there's a little issue with step 3 GDP. Like to be super blunt, in a lot of the problems that people were solving on homework 5 or maybe 4 and 5, a lot of people wrote this down, the thing that's in the yellow equation that's boxed in white. People wrote that down not all of you, as a step three in problems where you were being asked to solve for an instantaneous velocity. Now, I want to pause on this for a moment. Like, this is not what I'm about to say. I mean, it is a constructive criticism, but I don't mean to shame anybody. I totally understand why people did that. And again, but I'm asking you to correct it or hear me out and correct it and do it a different way. And then you'll get all the points. So this is not a punishment or anything like that. But, and I understand that way. So a lot of people wrote this equation down somewhere a bunch of times, like in their step three in their homework. Now, what I'm here to say is like, that's not actually an equation. Like, well, it's not a GDP. It's not a place to begin your thoughts. First, as a sidebar, I never said anything like that in class. I'm not saying it's not true, by the way. It is true. So this is a subtle thing I'm about to say. It is true. And if you wrote that down, you probably got the answer right, and that's great. But let's be really careful. I never said anything about that in class. So number one, to write it down presumably means you got it from the internet or remembered it from high school. Fine. That is not cheating. That is not cheating. The internet, I mean, you should use the internet. But when you use the internet or notes from anywhere else, you want to use it or them to help you understand, to give you a hint or help you understand something better or teach you something that I did not teach you effectively or that like whatever didn't work for you the way I taught it. So you can totally go on the internet and look for things and stuff like that. But then they have to make sense to you. You can't just write something down. Just you can't assume something is true, nonetheless understandable or meaningful just because it's on the internet. This is what happens to be true, but I don't know if everybody's understanding what it is or where it came from. If you're so first of all, you want to get in the habit of anything you get from the internet or from old notes, you have to make sense of it. It has to make sense to you. And I would argue this. This by itself does not make sense. In fact, it's confusing. This looks like some kind of, well, and also let me say, why did anybody do this? You're not crazy to do it. You did it because you thought you were looking for a V and you were smart enough. Any of you who did this were smart enough to know I'm looking for a V, but I'm not looking for V bar. I don't want an average. I want instantaneous. So how about I write this down? Okay, that's all reasonable. You were looking for a V, but you can't, but this is a step four, not a step three. And I'll tell you why. The fundamental thing that this came from, the definition is a definition of acceleration, of average acceleration, written up here in the white, off to the right here. This is fundamental. What do I mean by fundamental? I mean, it's always true, first of all. Second of all, it makes sense because it's a definition. It's what we mean by average acceleration. Like we mean the change in velocity per time. Acceleration is the speed of the speed, the rate at which you change your velocity as the clock ticks. This is not discovered for certain conditions. It is just the way we use language for all conditions. That's the fundamental concept. The concept is average acceleration is defined to be a change between one instantaneous velocity and another. Now, that's what I would write as step three. Now, if we're looking for V in a certain problem, fine. Then in step four, we rearrange that algebraically. Like we multiply both sides by T and add V naught to both sides. Fine. And then we get V. And we write that, we get the thing that you wrote down. And then we plug in the numbers and everybody wins. This is an example of where again, you might think that's a big waste of time. Like I know V equals, what is he like? Why? Come on, man. Why can't I just write down V equals AT? Because especially if you're saying it worked, I got the right answer. Yabberbound, leave me alone for heaven's sake. I got a life to lead here. But here's the deal. It worked in this easy case where you knew what you were doing. What that habit that you're getting into by writing that down will not work for you in the hard cases. And here's what's bad about the habit. Like V equals AT. First of all, it looks like it's a definition of V. Like it looks like, oh, whenever I want V, that's what I do. Like whenever I'm looking for V, like what V is not that. But V by definition is the first derivative of position with respect to time. V by definition is an AT plus V. For example, that won't work if you don't know anything about A or something like that. That's a consequence of the original definition. What I'm trying to say is we could have just as easily said, here's an example where doing that would serve you badly. let's say the exact problem was given to you. You were given the A, you were given V naught and all that, but instead of giving you the time and asking you to solve for V, say they had given you the V and asked you to solve for time, like same numbers, all that. But say you were being asked to solve for time. I would strongly suggest you're not going to find an equation for time on the internet that looks like you're not going to find, there isn't one. Well, I mean, maybe in some, dark underground crazy site where they sell like black market equations, but like there's not an equation for time and no one's ever memorized it or should memorize it. And even this one, no one should be bothering memorizing or something like that. If you memorize this, if we started treating this as a real equation, then we would treat the equation for time as a real equation, and all the rearrangements we would treat as reequations all the rearrangements we would treat as memorizable equations. And then we would do that for every single equation, no matter how many different ways we could arrange it. We would treat them all like a list of equations. And that's what physics looks like in high school sometimes, with all respect to all the teachers and of whom I have been one for many years. So I'm not saying it about, but like when physics intimidates people is when it looks like this enormous list of crazy, all these different equations that people feel like they have to memorize and keep straight, or even if they're given an equation sheet on a test, they're like, which one do I use when? Okay, I'm going to use this one here. Oh, I'm solving for V, so I'm going to use this one here. That gets people into trouble in physics. That's not really what physics is about. It works to a certain point, and then once the equation list gets too long, it falls apart. What I'm suggesting is, no, you don't have to memorize all these different equations. You don't have to view, they're not formulas. This is why I don't like the word, they're not recipes that just got taken out of like some wizard's bag that now like we just accept and we use whenever we need a certain recipe. They're not formulas. They're equations. They're statements of truth that we want as few of them as possible. Physics is the search for as few statements of truth that generate the most possible applications and informations as possible. So what I'm saying to everybody, I'm not yelling, but this became a very big and fruitful discussion in the other class that I'm just sort of, I don't know, summarizing right now. It sounds like I'm being super picky, and it sounds like I'm being maybe shaming. I don't mean to be either one. I do mean to be picky. I don't mean to be shaming. I'm saying get in the habit, especially when it's still sort of not so hard, get in the habit of starting when you get to step 3, write down something that's fundamental. Ideally, a triple equal sign. It won't always be a triple equal sign, but it will often be. Write something down that literally makes sense to you even before the problem starts. Like I would suggest that this V equals AT plus V naught. Anybody who I don't think it like people are walking around thinking like, oh yeah, I get that. Like people are walking around going, I know that, but they're not walking around going like, I get that. That's intuitive. But the other thing, A bar equals V minus V naught, you have to keep staring at it until you get it. Like you'll get it at a certain point. And if you don't, that's where you should be focusing your attention is like, get that it's just saying acceleration is the change in velocity per time. Change is subtraction, difference on the top. Like GDPs should be things that actually make so much sense once we think about them that we don't even have to artificially memorize them. We just naturally start remembering them once we get them. But we don't want the list to be too long. So, all right, I think I've said my piece. Again, if you did what I'm saying, anybody who did what I'm saying, anybody who committed the error that I mean, was doing homework very, very responsibly and thoroughly. Like no one, like so it's only it. You're all successful students. If you're one of the ones I'm talking to, but I'm saying from now on, and you can ask me privately if this doesn't make sense. The GDP is something that's like on a list that we're generating. The permutations and the variations on GDPs are what you do in step 4. And then you plug in numbers at the very last minute. That's how to do physics. Bottom line, and I'm saying this after years of getting myself in trouble. Physics was hard for me too. I mean, it is hard for me too. But what I've learned is that when I panic in the middle, or when something slightly stressful in a homework problem or an exam problem, what I tend to do is quickly search for what I think the problem is looking for. Like if the problem's asking for V, I'm like, okay, I need an equation for V. And then I like look for one and I try, but there isn't always one. Instead of searching for something that you think is relevant and then trying to warp it and make it true, which is what we all do when we get stressed, get in the habit of writing something true and then try to make it relevant. That's the big secret. Write something that is true and that makes sense, even if you don't see immediately how it links. If it's vaguely on the topic and it's true and it makes sense, like A bar triple equal sign V minus V naught over T, write truth down first and then try to manipulate it into being relevant. Don't write something relevant and then try to manipulate it into being true. Okay. All right, that's enough. So we have this list so far of the GDPs, but then three more equations got generated at the end of homework 4 and through homework 5. So here's what happened to summarize. At the end of homework 4, now again, everything I'm about to say now was in the videos that I asked you to watch. So I'll try to keep myself concise here or non-redundant. But hopefully this will just reinforce something that, sorry, that you already watched. Okay, so the last problem on homework number 4, there was a bunch of lists of numbers. There was a bunch of lists of numbers. And you were asked to get the average for each list. It was assumed or expected that you would just take all the number for each one that you could, no matter what list you were looking at, you could take all the numbers, add them together for a given list, add them together and divide by the number of numbers and thereby get the average. And that would work every single time. And that's called taking computing an arithmetic mean, a mean, like the mean average, the number that best represents um, the whole set. But it turned out, if you looked at those different lists, some of those lists lend themselves to a faster trick that you could have done in order to get to arrive at the same average. What you could have done with some of those lists, you notice, you could have just picked it with some of those lists. You could have just picked the number right in the middle. And it turned out to be the same as adding them all up and dividing by the number of numbers. Or if the list happened to have an even number of numbers in it, you could pick the number that wasn't that you didn't even see, but that was like right in the middle between the two printed middle numbers. That worked for some of the lists, but not all of them. Upon consideration, what you find is well, first of all, it's impossible to see that or even talk about a middle number unless you first make sure to rearrange any given list so that the numbers are like in an ascending or descending order. But you're allowed, but averaging means adding, and adding is commutative. So there's no reason you can't take the list and do that. But once you take the list and you put them all in an order, then even when they're all in order, only some of the lists lent themselves to this insight and some did not. The lists that lent themselves to this insight, to this trick, this shortcut, the lists that lent themselves to that were the ones where the numbers were changing, but by an unchanging amount. Right now, in all of the lists, there was change. All the lists were lists of various numbers. Otherwise, none of this is interesting. I mean, you could take a list 4, 4, 4, 4, 4, 4, 4, and ask what the average is, but like it's obviously 4. I shouldn't say obvious, but it's 4. Yet we're assuming a bunch of lists where numbers are changing. What we notice is, yeah, they're changing. All the numbers are changing. Like we have lists like 1, 3, 5, 7, 9, or another one, 1, 4, 9, 16, 25. The numbers are changing, but in the case where the numbers are changing by a constant amount, and only in the cases where the numbers are changing by a constant, like a steady step, in those cases, the mean number was the same as the median number. The number you would get by adding all up and dividing by the number of numbers turned out to be the same as the one right in the middle. Now, again, notice my care with triple equal signs versus double equal signs. This is kind of like the care that we must take to distinguish between step 3 and step 4 of a problem. Like the definition of mean is not the same as the definition of median. They mean two different things. They signify two different things. But sometimes they can work out to land on the same numerical value. When is that sometimes? The sometimes is when numbers are changing by an amount that itself is not changing. So for example, 1, 4, 9, 16, 25 is not such a case. It looks like a pattern, like it is a pattern. It's a very definite pattern. You could predict all the rest of the numbers. If I go 1, 4, 9, sorry, yeah, 1, 4, 9, 16, 25, you know the next number is 36. I mean, if you look at it and think about it. So it is a pattern, but it's not an example of the kind of pattern I'm talking about here. I'm talking about a list like 1, 3, 5, 7, 9. And what's the difference? The difference is that the latter list, each time I'm adding 2. I'm not I'm not adding a formula, I'm not adding a rule, I'm adding literally the number 2. Right? Or if I have a list like 20, 15, 10, 5, 0. I mean, it can go down and it could be and it could even be like a weird fraction or decimal. But the point is, if I'm always increasing or always decreasing by the same amount, then the mean equals the median. Now that's just a statement. Oh, and why, by the way, why? Well, because I'm always increasing or decreasing by the same amount. So the number that's in the middle does best represent the whole because everything above it is as much above it. Wait, the amount that everything above it is greater than it is the same amount as the amount by which everything below it is lower than it. That was almost not English. But I'm saying, why is the average of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? Sure. Why is the average of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? Why is the average of that 6? Like, why do I not have to add up all those numbers and divide by 11 to get 6? I mean, I could, and if you do, you'll get, if you add up all the numbers, you'll get 66, and you'll divide by 11, you'll get 6. But how do I know that right off the bat? How do I know that 6 best represents the set? Like if those were test scores, well, that's outrageous. But why do I know that 6 best represents the set? Because 7 and 8 and 9 and 10 and 11 are all off, are all wrong, are all deviations from 6 by exactly the same amount as 5 and 4 and 3 and 2 and 1 are, because the step never changed, right? So when the step never changes, when we're changing by a constant amount with raw numbers, we can trust that the median and the mean turn out to be the same. Now, I would not care at all. This is not a math class as such, except that this has such huge relevance to physics, to space and time. If instead, if each one of these numbers in a list represents an instantaneous velocity, like something you're seeing on the speedometer of your car at any given moment in time, if the numbers represent the dependent variable of velocity, instantaneous velocity, and if the independent variable is time, then we can apply this notion to velocities and say that if the velocities are changing by a constant amount, if they're changing, but they're not changing the way they're changing, if velocities are changing, but they're not changing the way they're changing, obviously I'll give you an example in a second, then so if acceleration is a constant, if the numbers are growing or shrinking by a steady interval, then the mean velocity does equal the median velocity. Put another way, V bar, the average for the whole thing, the whole interval, is the same as the instantaneous velocity right at the middle of the time. And the English I just said is captured by the equation I wrote here in white, but I'll make that translation in a moment. What I want to emphasize again is the whole purpose of this equation. Well, as the blue says, the whole purpose of this discovery, the utility of this observation is that up until now, we've had like 2 types of velocities, two types of measurements that we're always distinguishing between. We're distinguishing between averages that apply to intervals between 2 points of space and time versus instantaneous quantities that apply at 1 point of space and time. We always are running back and forth between these 2 types of quantities. Remember, the virtue of the average is that it's much easier to picture, observe, measure, and compute. An average is easier to picture, to measure, and compute. The disadvantage is it's just an average. It's not accurate at any given point. It just captures a trend overall, right? So there's averages that approximate a trend over some interval. And then there's precise instantaneous quantities that have the virtue of capturing something, of capturing a precise quantity or measurement right at one point in space and time. But the disadvantage is they're much harder to think about, to measure, and to compute. So we're always going back and forth between these two considerations. And what we now have is a discovery that allows us fluidly to get from one to the other. What we're saying is, in the case of in the case of constant acceleration, if and only if the velocity is changing, but in a steady way, then the average, the v bar that describes the whole, is the same, not by definition, but by discovery, is the same as the exact instantaneous velocity, one moment. What moment? One special moment, the moment right in the middle of the time. That's what we're saying. Not all moments. I mean, all moments, there's all these different velocities. Otherwise, this whole discussion is unnecessary. But if you have something where the velocity is changing fluidly, continuously from one moment to the next, you have an average for the whole thing. The average doesn't tell you the individual velocity at any given moment. But what we're now saying is, but it does tell you the instantaneous velocity right at the middle of the time. That's a special velocity that equals the whole average if and only if the acceleration is constant. And the way to write that as an equation is what I've written right here. How does this equation capture anything that I just said in English? It captures it because if you translate it, it's saying that V bar, the average of the whole thing, is the average of two particular velocities, the very first and the very last. If you take the very first velocity, VR, and you add it to the very last velocity and you divide by 2, you're averaging the endpoints. Remember, you're taking the lowest and the highest, adding them together and dividing by 2, as in the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I want to know the number that captures the whole, what I could literally do is take 1 and 11, add them together, get 12, and divide by 2. Why 2? Because I just averaged 2 numbers, 1 and 11, right? So it's saying the average is an average, so to speak. The mean is the median. It's a double equal sign. It's not the definition of average. It's not always true, but it's true under this condition. So it's saying, if you're ever trying to translate back and forth between an average and an instantaneous, so secretly, I'm saying there's information in this equation that's not obvious unless you listen to all of this. Like, it's literally telling you the average is the middle. And the middle you get by averaging the endpoints, and you can skip all the stuff in between. Why can you skip it? Again, because everything that you skipped on the one side of the middle is exactly the same deviation in one direction as everything you skipped on the other side of the middle in the other direction. So they cancel each other out. So that's a new equation. We're calling equation. That's a new GDP now. Now it's not a triple equal sign. If you ever were to write this down as a GDP, you'd have to first write if A equals A naught to make it so that it's a principle or a truth. But I'm giving a little F. It's like our 6th real possible equation that you can use as GDP, and it's very powerful. And it's subtle because, and I'm going to move on in a minute, but notice it's the first GDP we have that isn't a triple equal sign. So it's less obvious than the others, or I don't know if obvious, it's less self-evident than the others. And one big hint about this one, it's the first one that I'm suggesting to you, that when you're stuck on step 3 ever in a problem, or you're stuck on a problem and you've set it up and you've drawn it, and then you write step 2 down what the problem is, and now you're like, all right, so I don't know. I mean, I'm looking, I don't even know what I'm looking for, right? Well, the first thing is, I mean, if it has anything to do with velocities, you're never wrong in writing down the other equation for V bar first. I mean, notice this. We now have 2 different equations for V bar. If you just memorize equations or just start thinking of them as recipes and formulas to plug into, it's possible you'll get in trouble because it's confusing when you realize we have 2 different equations for average velocity. I mean, 2 different equations where the left-hand side is V bar. What I'm telling you is here's how to distinguish between them. First of all, when in doubt, always write the other one first, because that one is never false. Always write the other one first. I mean, even if you don't end up using it, it's still true. You'll still get points for it. It's not going to hurt anybody. But then if you're still stuck and you know the problem has something to do with velocities, but you just can't seem to be going anywhere, when in doubt, if nothing's coming to mind, I'd suggest you consider this one because this one generates a lot more than it looks like at first blush. This one is an implication of average velocity, that the average is the average of the first and the last under certain cases. The weirdness of all this, and then I'm going to move on, is that what I'm really telling you now, and it's subtle, is it's the thing that a lot of people did wrongly, incorrectly on Grandma Grimm and on Hilfiger. At first, people thought, oh, to get average velocity, I'm just going to average two velocities. And then I made a big stick and said, I never said you could do that. We never said you could do that. To get average velocity, first and foremost, you take displacement, divide by time. Now I'm saying, well, sometimes you can average two velocities if you want to get average, sometimes. But Grandma Grimm and Hilfiger were not one of these times because in Hilfiger, you did not have, in neither of those problems did you have constant acceleration. Like first you had acceleration of zero, then you had acceleration of something, and then you had acceleration of zero. That's not constant. So it blew, so we didn't have the right to anyway. But I'm saying now from now on, yes, this equation means you can average the two extreme velocities to get the one in the middle if accelerations are constant. Okay, so that's an equation now. And of course, we'll put it into practice. We do put it into practice in homework 5. I don't know if I'll get to those problems today. I'm going to move on. Wait, let me just quick check. I know I've been talking a lot, so pause for a second. Any issues, questions at all? So when Gabriella's still with me, I love it. Okay. Everybody's still with me. Okay, thank you. But either ask a question in the chat about anything I've just said, or give me a thumbs up that I can like move on to the other two equations. Okay, thumbs up. Thank you. Thank you. All right. Awesome. Awesome. I see. Okay, great. Thank you. All right. So I'm moving on. Okay. Great. Thank you. And you can put your hands down now. Okay. So now we want to sort of, I know we have a half hour. We want to derive two more equations. Now we're going to derive them, meaning they're going to be double equals. Then we're going to derive them from the equations we have so far, from these three that are at the bottom, the yellow. Like those are all now knowns. One of them is a double equal sign because it's only true under a certain condition. Therefore, anything we derive from it or from the other two is also only true under that condition. So this condition is really important now. In fact, so this condition, constant acceleration, that's what lab 2 is all about. And again, like I said before, any new last equations we're getting today, formalizing, they all count as a list that you could ever look up on the web or in a book called constant acceleration equations. They only apply if you have some value for A that isn't changing. But now it turns out there's tons this is a very important condition in physics. It's very specific, but the condition happens to be met a lot of circumstances in physics. The calculus thing that I'm saying is that right now what we're studying in physics is cases where there is a second derivative of position with respect to time, but there is no third or higher derivatives. Like if you were sort of starting to understand calculus, hopefully that will make some sense to you. I'm saying we're looking at cases where the second derivative, where d2x dt squared equals some number, literally some number, not equation, some number. And therefore d3x over dt3 equals 0. That's what we're looking at. Now, that sounds very obscure. Like, why do we care about that so much in physics? Well, for one thing, because it happens on the surface of the Earth all the time. What you're trying to see in lab 3 is that lab 3 is this very special case that almost sounds like a contradiction at first. Lab 3 is a case of constant change. Let's think about that consciously for a minute. Because if you just accept it on faith, eventually it starts seeping into your unconscious as some very murky contradiction. I mean, it sounds like a contradiction. Constant change. Constant means staying the same. Change means not staying the same. What the heck is constant change? What we're saying is something that increases or decreases its velocity, something that does change its velocity, but in a steady way. What you're trying, like for example, a car that's going 10 miles per hour, 20 miles per hour, 30 miles per hour every minute, like it's changing, but if every minute it's not gaining some wild or random or patterned amount of miles per hour, it's literally always gaining 10, for example. Or in the lab 3, you're looking at what it turns out to be an observation or a finding that when you stand at the surface of the earth and drop something, when you drop something, it changes its position every moment. It does. Like you drop something, first it's in your hand, then it's lower than your hand, then it's lower than that, then it's lower than that. It's changing its position every moment. Also, so therefore it has velocity when you drop something, whether it's a string with a bunch of bolts on it or just one bolt or whatever. When you drop something, there exists a first derivative of position with respect to time. An object velocitizes. But also, it turns out, whether we knew it or not, it doesn't just move when you drop something, it also changes its velocity. That may or may not be obvious, but it's true. How do I know it's true? Well, at first, it's in my hand, it has velocity 0. But then I let go, so then it has velocity something. So its velocity is changing, right? So it's not just moving when something falls, it's not just velocitizing, it's changing its velocity naturally, automatically when it falls to the ground. So that's called acceleration. Right now, if you understand calculus at all, if you understand, oh, okay, I get it. There's a dx dt. There's a derivative here. There's a rate of change. And then you get, oh, I see there's also a rate of change. There's a rate of change of rate of change. There's also an acceleration, a d2x dt squared. You might quite reasonably think once you're getting the math that, oh, maybe there's a change in the change in the change. And even if you think that's a ridiculous thing to think, people in English tend to accidentally think that all the time. They tend to talk about, oh, it's speeding up its acceleration. People will say that all the time when they're doing lab 3. When something's falling, they'll start talking about the change in acceleration or it's speeding up its acceleration. Whoa, 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 be careful. What we're trying to discover in lab 3 is that even though there is a velocity, dx dt, and even though there is an acceleration, d2x dt squared, there is no change in that. What all of the bolt manipulation and the backwards weird reasoning, and it is hard. It's like a very like unexpected, it's like simple but hard lab 3. I mean, not doing it isn't hard, but like understanding it is hard. What we're trying to get across to you in lab 3 is that if your string works, if you finally come up with a pattern of bolts that actually hits the ground in even time, in even rhythm, that must mean you must have arranged the bolts in a certain kind of way, in fact, what turns out to be a quadratic way, in a like bolt, in like a bolt. The first bolt is at 0 at the edge, and the next bolt is at some unit, like 1 centimeter or 5 centimeters or 10 centimeters, whatever. And then the next one has to be 4 units, four bigger than that first unit. And then the next one has to be 9 bigger than that first unit, and then 60, whatever that unit is. In other words, it turns out that the bolts have to be arranged in the perfect squares in order for them to hit the ground in even time. What does this mean? Who cares? What is it? It means, once you go through all the reasoning, that the bolts must be accelerating, but at a constant rate. They must be gaining speed, but not gaining in their gains. They must be getting faster and faster by an unchanging, steady amount. Now, it turns out, you might know from high school or from living in the world that amount, when you use meters, that amount can be called 9.81, approximated as 9.81 meters per second squared. That's fine. And yes, that's a super useful number ultimately, but that's not really the takeaway of the lab. Don't memorize that number and think that that means you understand gravity or constant acceleration. The significance is not the number. That number is only the number that we get if we choose to measure in meters and seconds. We could choose to measure in feet. God is not choosing meters. I mean, I don't mean that facetious, like Mother Nature, Father Time, they don't care about meters. We just made up meters. We could just as easily measure in feet. I mean, they're convenient. We like meters, but we just made them up for our own convenience. Because they're based on a 10. You might say, well, but wait a minute, they're base 10. Like base 10 is special, right? Like they're better than feet, for heaven's sakes. Feet aren't in base 10. They're better in base 10 because they're more convenient in base 10 because we like base 10 because human beings happen to have 10 fingers. End of story. Like there's nothing divine about 10. Anyway, what I'm saying is we could just as easily have measured in feet or cubits or something, and then we get a totally different number. If you measure in feet, you get 32 feet per second squared, et cetera, et cetera. So the specialness is not the number. The specialness, the finding of lab 3 is that there is a number, that the number doesn't change, that it isn't 9.8 the first second and then 19.6 more the second and then more. There's no more and more and more. It's just every second we increase not where we are, but how fast we're going by a certain steady amount. Okay, that was off a little bit, but that's what you're writing about in your formal report for lab 3, which I believe, at least in some sections, is like due next. So I don't know if that helps or not, but that's the point, is that for the string to have to be arranged in perfect squares positions, that must mean that the acceleration is a constant. Why does it mean that? For reasons I'm going to say in 18 minutes at the end of this lecture. So tune in. Like, well, what's a perfect square have to do anything? That's like the final conclusion of this lecture. What I'm going to say now is that if you want to derive another equation that we use for the rest of physics for cases like, for constant acceleration cases, such as anything falling toward the surface of the Earth, then what you do is you take these three equations that we have and you smosh them together algebraically. You go like this, except, let me make a correct, except I did something a little bit weird at the, hold on. I just want to bear with me for a second because I know this got wacky in the other class. Yeah. So I'm just gonna, hold on a second. And if you happen to have friends in the other class, if you in the other class by accident, I derived the equations like out of order. It still all worked out, but it was a little confusing because I went out of order. So if you have friends in the other class, you can tell them that I rearranged it for your class. I fixed it for your class and fixed it in the notes. So if they look at the PDF, it'll be correct in the PDF. Anyway, what I'm saying is this. Um, okay. What I'm saying is we take the three equations that we have and we're going to algebraically like put them together. Um, and even in like the homework, this is what you do. Like you write down like what's true first. I wrote down what's true. Now what am I looking for? I'm looking for living now in a wrong place. I'm looking to get x or x minus x naught as a function of t. Like what I want now, because I think it's going to be so common and useful in physics, I want a situation where as long as I know as long as I have constant acceleration, so that assumes I have a number for acceleration that doesn't change, and I know the starting conditions, like where an object started, maybe I call it zero, maybe I don't, and how fast it was going when it started. If I know the starting conditions and the constant acceleration, I want to be able to come up with a rule or a mapping or an equation relationship that for which time is the input, the independent variable, and position is the dependent variable. That may all sound like very obscure and specific, but really what I'm trying to come up with is like is an answer or a useful answer to the most basic question in physics, which is if you tell me the when, can I tell you the where? All of physics is about predicting or retrodicting where something is going to be when. It's all about stuff moving through space and time. Like literally all of physics is stuff moving through space and time, kilograms moving through meters and seconds. So, so the most fundamental thing I could ever ask in physics is if it's like where, like if you tell me how much time I am waiting, can I tell you where the thing is going to be? And that's all we were doing in the homework up until now. It's just now we're able to do it in a somewhat sophisticated circumstance where things are, I mean, it's easy when something's not even changing its speed. If you know it's going 30 miles an hour and it's going for 2 hours, where's it going to be in 2 hours? in 60 miles ahead, right? Now we're saying we can do that even in a more complicated case where the velocity isn't even remaining constant, where the velocity is changing, where there's acceleration, as long as the acceleration is staying steady. If you know the acceleration, you know how fast it's going at the beginning, and you know where it is at the beginning, can we predict where it's going to be when? Well, yes, yes, we can. We're going to derive position or displacement as a function of time. So I'm trying to rearrange the equations to get x minus x naught on one side and everything with t on the other side. So I write down what I know, and I wrote down I guess I'm a little redundant here. I wrote down the definition of acceleration. Okay, wait. So I'll show you where I am in what I'm talking about. I'm saying if I get to this step right here, right? Like if I'm saying, all right, x minus x naught equals average, like I rearranged the first one. So I said, fine, displacement equals average velocity times time. That's like what you used to hear in seventh grade is distance equals rate times time. Like that's, if you know that distance equals rate times time, like, yeah, that's what I'm saying. Although I'm saying that's really not very, you have to be more specific. It's really that distance equals average rate of speed times time, or displacement equals average rate of velocity times time. So that's, and that comes from the definition of average velocity, but that's what's right here. X minus x, or x minus x naught equals average velocity times time. But now I substitute in for average velocity our new finding that as long as acceleration is constant, average velocity is the average of the velocities. So I substitute that in. I'm in the boxed blue thing. And then I say, all right, so I'm almost somewhere. Like I've got x minus x naught on the left side. I've got t on the right side. Everything else seems to be a given or a known except v. Like v naught, we're assuming is given, but v is not a given. It's how fast the thing eventually got to by the end. I don't know that, but I could figure that out because I could rearrange a bar and get v equals at plus v naught. Right? This is the thing I was asking everybody to do in their step three. Like v equals at plus v naught is not a thing unto itself, but it is a result of the definition of average velocity. And note, I removed the bar from the a when I felt like it, because if you note up here at the top, if we're in constant acceleration, that means that A never changes. So whatever it is at the beginning is what it is at the end and what it is on average all the way through. So I can remove the bar. So I have V equals AT plus V naught. So I'm going to substitute that in. Oh, wait, I thought I rearranged these. Wait, didn't I rearrange these pages? What happened? Hold on. I could have sworn I do that again. Okay. What? Wait, didn't I? You just saw me. Wait, that? Okay. Sorry, I'm going to try this one more. I just don't want to. We have 11 minutes. We're fine. But aren't you witnessing me as I'm rearranging these pages? Why are they not? Hold on a second. Oh, I'm rearranging the wrong pages. That's okay. Right. Okay, I think this should be written. Okay. So we have this, right? And then we're saying this. This is no longer a backtrack. Okay. So, right. So I'm just, okay. This is like repeating where I was. X minus x naught equals v naught plus v over 2 times z, but I don't know what v is, so I rearrange a to get an expression for v. Okay, that's just all repeating what I just said. And so then I plug in for the v, right? So I have at plus v naught plugged in for v. And then I collect the like terms. I have 2v naught. So I have at plus 2v naught all over 2. And then, but that's all over 2. So everything can be divided by 2. So the 2's cancel on one of the terms, but not the other. And then and everything that gets multiplied by t, like the t gets distributed among the whole thing. So I end up with this equation, x minus x naught equals 1 f at squared plus v naught t, right? So, oh, thank you, John. Sorry, I totally missed like 20 minutes ago that thank you, John, for putting that in the chat that you understand everything I just said. I really appreciate that. And you should submit for points. And I'm sorry to backtrack now. It just shows you I'm not paying proper attention to the chat. Shame on me. Good thing I don't believe in shame, except on me. Um, but do I believe in me? Good question. I'll get back to you as soon as I find out who I is. Okay. So the equation that we just derived here is x minus x naught equals 1 f at squared plus v naught t. That is huge. Okay. Notice I'm even labeling it with the letter F. Like that's like now our sixth. That's fair game from now on in for GDPs for step three. It's not a triple equal sign. It's not uh, a definition. And it is only true if you have some value of A that you can plug in. If you have more than one value of A, what do you, it's not true. Um, but it is fundamental and huge because from now on, it is literally, that is illegible. That's supposed to say, I buried the body under the bridge with 40 unmarked bills. Sorry, that is so offensive. Position function of time is what that's supposed to say. It's 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 fundamental in physics. Anytime for constant acceleration, such as free fall. Like this totally works in free fall. In free fall, it happens you might plug in the number 9.8 for A, or you might be on the moon and plug in 1.16 or something like that. But free fall is totally an example of a situation where this equation is quite applicable. Now, so and again, in problem solving terms, you use it when you know the time, when you know the acceleration, when you know the initial velocity, you know the initial position. Often the initial position is zero, but not always. When you know those things, x naught, v naught, and a, and you're looking for a mapping, a relationship between time and position. Okay, that's when you use this, and that is quite often true in physics. And of course, it can be rearranged to find other things, as is the case in Big Old Duck. I mean, one warning about the Big Old Duck problem. The Big Old Duck problem is it's all about this equation, but even there, it's already assumed that you've gotten enough practice or you're used to this equation enough that you're willing to rearrange it to solve for time in the Big Old Duck. In fact, that's a big hint of how to solve the Big Old Duck. You want to solve for time first by rearranging this equation. And that is not easy. And that is not a memorizer. Like, don't even look up time. There's no equation for time like on the internet for cases like this. And I'll even go a step further and give you a hint. In order to rearrange for time, notice this is quadratic. Like you got a t squared in there and a t. So you can't even just do simple algebra to get the t. You're going to have to use the quadratic equation. Oh my God. Oh my quark. That's a big hint. Don't be, I mean, and if you don't follow the hint or you're not up to it yet, don't worry about it. But I'm saying this equation's so fundamental now that even rearrangements of it are expected. And if we try to memorize all the rearrangements of this, our list would get way too long and we wouldn't be able to do physics. So anyway, so we'll practice it more. And you obviously you do practice it in homework 5, and I'll get back to that next class. But that is the position function of time. Lastly, is the last equation. We could start the same way. We can just say displacement we could say again, displacement equals average velocity times time. That's what we're saying here on the top, right? Now that again, that's not a memorizer. Don't memorize that, but that's a rearrangement of fundamentals. On the other hand, I hope it makes sense. I mean, displacement equals average velocity times time. It's like saying distance equals rate times time. But then here I'm going to rearrange for T. In fact, let me slow that down and show you how I did that, because I think that's the page that got erased. Or I mean the page, yeah, that's the okay. So what I did, let's say I want an expression for T. And again, this is not something you'd find on the internet. I could say, well, A bar equals V minus V naught over T. I can multiply both sides by T. I can get rid of the bar because acceleration is always the same in this case. So we go like this and then divide both sides by A, right? That don't memorize that, but it's true. Um, so that I could then substitute in for the T up there in the X in the yellow. Now, why would I do that? If I want to get rid of the T's, is that I would do that. If I don't, if I want to get rid of the T's, I would substitute that in. So then I have V plus V naught over 2 times V minus V naught over A, and then FOIL out the and then when you're multiplying fractions, you multiply the numerator and you multiply the denominator. So the denominator is just QA. The numerator, I FOIL it out, and these things cancel, right? So I get V squared minus V naught squared, like the difference of two perfect squares in the numerator, all over 2A. So what is it? So it looks like gobbledygook. That equation looks more like gobbledygook than any of the others to me personally. Like it's not like I look at that equation and go, oh yeah, I could see why that would be true. No, I just look at it and go, oh, okay. But why is it useful? Why do I care? Like again, I could do all kinds of permutations of these equations. The reason that one's useful is precisely that I got it by getting rid of the T. This is when you don't know, whenever you have a situation, a constant acceleration where you don't know the time and you're not solving for the time. Hey. Any constant acceleration situation, and I see there's 2 minutes, any constant acceleration situation for which you're not given the time, any information about the time, and you're not solving for the time, like where time just has nothing to do with it, that can be an intimidating situation. And yes, if you're very careful, sometimes you could like solve for the time and then use the time to get, but sometimes that doesn't work because sometimes things are simultaneous. So you'd have to like do two simultaneous equations and solve them. And that can work. But what we've done here in effect is done the two simultaneous equations once in advance. So we never have to do them again. So we're saying now this final equation, don't memorize it, just get used to it or whatever. Or just have it handy. This is an equation you use for constant acceleration when you don't know the time and you're not solving for the time. We're calling it equation G, i.e., it's the seventh acceptable thing to write down as a step 3 GDP. So we're going to practice these next Monday. Oh, and Monday, we'll get back to literally. So Wednesday, big old duck, the homework 6 is due. We'll catch, and then Monday, we'll start going over it and all that. But I say Monday because Wednesday, the video that you watch um, is more Galileo's principle of relativity. It's like form number 4. In other words, it can stand alone. If you're having issues with the homework and you want to ask me questions, if it's better to do that live, so we'll do that live Monday, in real time. Wednesday, the video you're going to watch is Galileo's principle of relativity, form number 4, which starts making the principle of relativity far more mathematical and relevant to your next couple of to lab 3 to lab 4 and etc. and homework 7. So I'm done. Have a lovely, lovely weekend. And we're not meeting Wednesday. Well, yeah, I just said that. So have a lovely weekend. I'll hang out for a couple of minutes for questions or whatever. The recording will stop. But Quark bless America.